Hi kids, back today. I know this is quite involved. That's okay. We're going to be patient, take it slow. So nothing new today. I'm just going over some of the homework that I assigned yesterday. So we're in section 3.4 and we're with practice question 3. And it says determine the appropriate coefficient of friction. So we're mu, the coefficient of friction in each case. So it takes 59 newtons of horizontal force. So I've drawn a free body diagram here. So it takes 59 newtons of horizontal force to get a 22 kilogram leather suitcase just starting to move across the floor. So I've drawn a free body diagram. It's a 22 kilogram object. There is a horizontal force of positive 59 newtons. I'm making this direction right here positive. It's on the planet Earth, so there's the weight, the force of gravity on it, which is equal to the mass of the object times the gravitational field strength near the surface of the Earth. And as we know, that's negative 9.8 newtons per kilogram. There's also the normal force holding the object up from the surface, and we know that the normal force is equal in magnitude but opposite in direction to the force of gravity. And against it is the force of static friction. The reason it's static friction here is it's just starting to move. It's not moving. The acceleration is zero. It's static friction. That's why our required to calculate is mu s. Speaking of friction, we remember the equation from the other day. To find the force of static friction, we can calculate the magnitude only. That's all we have. Magnitude of the force of static friction is equal to the coefficient of static friction times the magnitude of the normal force. So what are we trying to calculate here? We're trying to calculate the coefficient of static friction, mu s. So if we take a look at this equation right here, there it is. There's the variable we're trying to solve for. If we know what the force of static friction is, and if we know what the normal force is, with these two being known, we could rearrange this equation and solve for the coefficient of static friction. That's what we could do. So let's go about trying to find first the force of static friction. Now, as I said a long time ago, we're in the dynamics section of physics where we are studying the causes of forces, and the causes of forces, it's causes of motion, and the causes of motion are forces. So when we solve dynamics problems, F net equals ma, Newton's second law, and F net is equal to the sum of all forces acting on an object, also part of Newton's second law. This is the very heart of solving these problems. You write down F net equals ma, you write down F net is equal to the sum of all forces, and it is the key that will open up the solution to many of these dynamics problems. So here we go. Analysis A, for finding force of static friction. We write down F net equals ma. We write down F net as the sum of all forces. So what are the forces acting on this? Well, we look at the free body diagram. There is force horizontal push, 59 newtons. There's the force of static friction. There's the normal force. There's the force of static friction. These two, that's an error. Let me fix that, kids. That should be a G. That's a horrible G that I've drawn there. So let me start again so we don't have any confusion. Okay, all the forces acting on the object are the horizontal force, 59 newtons, the force of static friction, the normal force, and the force of gravity. Looked like an S there, but it was actually a G. I should probably fix it down here too. Make that look like a G. What's up, G? So, as we know from the past, these two forces cancel out. So all that is left is that the net force is equal to the horizontal push force plus the force of static friction. There we go. Force of static friction. I got to make my G's and my S's better. These are the only two that remained. Force of static friction and the horizontal push force. So, since the object is not moving, I have mass is 22 kilograms, acceleration is 0 meters per second squared. If I multiply these two together, I get an F net of 0 newtons. I can now take that information and put it into this equation in here, that the net force is equal to the only two forces left, the horizontal push force and the force of static friction. So I substitute in the values. 0 for net force, positive 59 newtons for the horizontal push force, and force of static friction is left here. I now bring the positive 59 to the other side, and we have left that the force of static friction is negative 59 newtons. So now I have solved this. So it's now solved, part one. So now I can move on to part two, figuring out what the normal force is. Well, we know that the normal force is equal in magnitude but opposite in direction to the force of gravity. And we know the equation for the force of gravity. It's the mass of the object times the gravitational field strength near the surface of the Earth. So let's substitute our values in here. Normal force equal, well, the minus sign stays. There's the mass, 22 kilograms. There is the gravitational field strength near the surface of the Earth, negative 9.8 newtons per kilogram. We multiply that all through and we get positive 215.6 newtons. It's positive good because it's upward. I like that. So lo and behold, kids, we have now solved the second part here. So now we know the normal force. We had just calculated the force of static friction. We can rearrange this equation. And we would get that the coefficient of static friction is equal to the magnitude of the force of static friction divided by the magnitude of the normal force. So now we can substitute in the values that we have. Now remember, magnitude signs means everything is positive. Even though it's negative 59 newtons here, it becomes positive 59 when we use it. And this is already positive and it would remain positive. So when we do our dividing, we get that the coefficient of static friction is 0.27. No units, just like on page 101. It's just each number tells us about the two surfaces involved, the surface of the object and the surface of the floor upon which it's being dragged. All right, now this is part B of the question. And in part B of the question, it says a horizontal force of 54 newtons keeps the suitcase that was talked about in part A moving at a constant velocity. So it's moving at a constant velocity. That means the acceleration is 0. So let's draw the free body diagram again. There's the force of gravity on it, also known as the weight. There's the equation for it. There's the normal force, the surface supporting the object. It's equal in magnitude, opposite in direction to the force of gravity. There's the horizontal force. Now this is different. It's 54 newtons. The object is actually moving with a constant velocity in this positive direction. Not like in part A where we were just trying to get it started to move. This is different. Okay, and because it's moving now, it's not the force of static friction, it's the force of kinetic friction that is operating here. And we know the equation for that, at least for the magnitude of it, that the magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction, which is what we're trying to solve for, and the normal force. So similar to our previous example, if I want to calculate the coefficient of kinetic friction right there, I need to know the force of kinetic friction and I need to know the normal force. So let's break it down step by step. Let's find a way to find the force of kinetic friction, number one. And that's what I've done over here. As I've mentioned in the other example, F net equals ma, and F net, the sum of all forces, is the key to unlocking the solution to many of these problems. So we write down F net is equal to the sum of all forces acting on the object. That is the horizontal force, the force of kinetic friction, the force of gravity, and the normal force. And we know that the force of gravity and the normal force cancel out. Okay, then F net equals ma. Well, kids, it's moving at a constant velocity. Acceleration is 0. So I can put a 0 in here, and it'll tell me that F net is equal to 0. I now can use that over here. So I just found out that F net is equal to 0, so I put a 0 in here. The force of horizontal push is 54 newtons. I put it in, and what we're trying to solve for remains force of kinetic friction. So I substitute, I rearrange, and now I have found the force of kinetic friction is negative 54 newtons. Negative 54 newtons. So I have found this part here, and that's one of the things we needed to solve for before we ever tried to solve for the coefficient of kinetic friction. Next, if we want to solve for the coefficient of kinetic friction, we need to solve for the normal force. Well, I'm going to do that for you. There it is, part 2, right here. Normal force is equal in magnitude, opposite in direction to the force of gravity, negative m times g. Just like in the previous example, I plug it in and I actually get the same answer. It wouldn't change, okay? And now I can rearrange this equation here, and I get the coefficient of kinetic friction, mu k, is equal to the force of kinetic friction divided by the normal force. I put in the values right there, negative 54 newtons divided by positive 215.6 newtons. But remember, these are in magnitude signs. So everything is a positive here when you key it into your calculator. And I get 0.25 as my coefficient of kinetic friction. Now 0.25 kinetic friction coefficient compared to 0.27 coefficient of static friction, that makes a lot of sense because the coefficient of kinetic friction will always be less than the coefficient of static friction. Okay, I'm back, kids. I just got an emergency alert on my phone, so I took care of that. As I was saying, the coefficient of static friction is usually always larger than the coefficient of kinetic friction, and you may have noticed that on the table on page 101 of your textbook. All right, practice question 4. I assigned that one as well. Let's go over it. It's by going through these examples that we really start to learn the details and the nitty-gritty of what's happening with friction and how it all works. All right? We're going to take it slow. We're going to be patient. If you have any questions, please ask me. I've established that question discussion thread that you can ask questions on. All right? It's on the announcement every day in D2L, so please do that. So, what does it say? It says that we have a 73 kilogram hockey player, so there's the mass, and the hockey player glides across the ice on skates. So I can look on page 101 to find the value of kinetic friction. I know it's kinetic because the skater is moving, sliding across the ice. Okay? And we want to find out what is the force of kinetic friction acting on the skater. So I'm going to put up my G for given. What's up, G? And what are the forces acting on this sliding skater? Well, we have weight, force of gravity acting on it. We have the normal force acting on the skater, which is equal in magnitude and opposite in direction to the force of gravity. And there is the force of kinetic friction slowing the skater down. Well, what did they ask us to solve for? The force of kinetic friction. The force of kinetic friction. We have an equation for that, or at least the magnitude of it. The magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction. Once again, kids, I got interrupted by another emergency broadcast there, so let's start again. The magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the magnitude of the normal force. So the next line, we keep the magnitude of the force of kinetic friction, we keep the coefficient of kinetic friction, and we realize that the normal force is equal to the negative of the force of gravity. The next line, we write down, well, what's the equation for the force of gravity on an object? Well, it's mg, right there. We still keep the negative sign. Now we can substitute. So the magnitude of the force of kinetic friction is, put in the coefficient of kinetic friction, magnitude sign, negative sign, the mass, the gravitational field strength near the surface of the Earth, negative 9.8 newtons per kilogram, bracket, and close off the magnitude. It's magnitude, kids. Everything turns out positive. So the magnitude of the force of kinetic friction is 7.2 newtons. But they didn't ask for the magnitude of the force of kinetic friction. They asked for the force. That's a vector. I need a direction. Where am I going to get the direction from? I'm going to get it from the free body diagram. There's no calculation here. You go back to the free body diagram, you realize that the object had a velocity moving forward, which we usually call positive. Well, then by default, the opposite direction, the opposite in which friction is operating, must be negative. Got it from the free body diagram. All right, I also assigned practice question 6. We'll go one at a time. So let's look at practice question 6A first. So let's read through this. We're in section 3.4, practice question 6. A worker of a moving company places a 252 kilogram trunk, so there's the mass of the trunk, on a piece of carpeting and slides it across the floor at a constant velocity. Hugely important here. Constant velocity means the acceleration is 0, therefore the net force is 0. And how is it moving? Well, there's a horizontal push force of positive 425 newtons. This direction we will deem to be positive. So in our given here, let's complete the free body diagram. Well, there's the weight of it, which is the force of gravity. So I've calculated it for you right there. There's the weight of this object, the force of gravity on it. There's the normal force on it. There you have it. There's the normal force. Okay, and the normal force is the positive of the force of gravity, just the opposite direction. So I have that there, positive 2,469.6 newtons. We're keeping a few extra significant digits until the very end. And we want to write down or write on the free body diagram the force of kinetic friction. Right there, the force of kinetic friction. All right, well, what's required? Required is the coefficient of kinetic friction. Well, there's only one equation that I know that has the coefficient of kinetic friction in it. Here it is. Magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the magnitude of the normal force. I rearrange it and I have this expression right here, which is great. Look, I want to calculate the coefficient of kinetic friction. I need the normal force to do that. Perfect. Check mark. There it is. I have the normal force. Bingo bango. All right, what else do I need? I need the force of kinetic friction. Uh-oh, X. I don't know what it is. I don't know what that is. But I do know how to calculate it. And that's what I did over here. As I mentioned many times now, the key to solving many dynamics problems is write down Newton's second law, the most important equation in physics, F net equals ma, and also the other part of the law that the net force is equal to the sum of all forces acting on the object. Well, on the object, there's the push force, there's the force of kinetic friction, there's the force of gravity, and there's the normal force. And as we've done many times now, the force of gravity and the normal force cancel out. So we're left with the net force is equal to the push force plus the force of kinetic friction. But, but, there's no acceleration. So the net force is 0. We can use that right in there. Net force is 0. We know the push force. We have our only unknown left in here, the force of kinetic friction. So we find that the force of kinetic friction is equal to negative 425 newtons. That's good because frictional forces are usually in the opposite or negative direction. So now I can put a check mark next to that. Bingo bango. I solved it. Okay? So I substitute the values in now. There goes in the force of kinetic friction. The normal force we got from the free body diagram. Remember there's magnitude signs here, so everything works out to be positive. And I have, by dividing now, I have solved for the coefficient of kinetic friction in this situation. All right, hopefully you followed me through that. If you didn't, all you have to do is ask a question in the discussion thread, and I'd be more than happy to help you. Next, 6b. What happens to the coefficient of kinetic friction if another 56 kilogram trunk is placed on top of the 252 kilogram trunk? Well, kids, mu k does not change when more mass is added on the trunk. This value here, mu k, it only depends on the object surface and the floor surface. If you look at the table on page 101, it says on that table, for example, Rubber on asphalt dry, 1.07. It doesn't say rubber on asphalt dry if you have like a little mini car, it's that value. It doesn't say rubber on asphalt dry if you have a transport truck on that. No. If you got rubber on asphalt, it does not depend on the mass of the object. It never changes. It only depends on the two surfaces involved, as table 1 on page 101 tells us. All right, kids, we're in the stretch run for today. This is the last bit for today, but I strongly believe by listening to me and following through these examples, you'll really start to get a deeper understanding of the force of friction and dynamics in general, and how we use free body diagrams, how we use Newton's second law. We're in one of the more critical parts of this course. So 6C says, what horizontal force must the mover apply to move the combination of the two trunks at a constant velocity? So right off the bat, they're saying, look, we have the original trunk and we put another trunk on top. So when I draw the free body diagram and I draw the weight or the mass, it's 56 plus 252 kilograms. So I have a totally more weight in here. It's got a weight of negative 3,018.4 newtons. The force of gravity has increased. All right. And the normal force then has also increased. It would be the opposite direction of the force of gravity. So I can actually calculate the force of kinetic friction acting on this object here. It would be the coefficient of kinetic friction, which does not change. This does not change. We talked about that in part B, and we actually calculated it in part A. It's still 0.17. What has changed is the normal force. It's heavier. Since there's two trunks together, it jams into the surface more. There's more contact. It pushes into it more, and we have more friction. So we can do this calculation here, and we get that the magnitude of the force of kinetic friction is 513 newtons. But we need to find the whole vector with direction included. So the force of kinetic friction is negative 513 newtons. We get the direction, the negative sign, by looking at the free body diagram. The push direction, the direction of constant velocity is positive, acceleration is 0, but the velocity is positive. Moving forward, that means the force of kinetic friction must be in the opposite direction. The opposite to positive is negative. So we're well on our way now. We've done all of this to get ready to calculate force push. That's what we've done to get ready to calculate force push. So, as I've said to you many times, and I'm going to repeat myself, the key to solving these dynamics problems is Newton's second law, the most important equation in physics, and one of the more important concepts that we have in this course. So we write down F net equals ma. F net is the sum of all forces acting on an object. So that would be the push force, the force of kinetic friction, the normal force, and the force of gravity. And as we've seen many times, these two cancel out. So we're just left with the push force and the force of kinetic friction. So since the acceleration was 0, we know the net force is 0, and we can plug in that value right into here. We can use that 0. Force push is our required, what we need to find. And our force of kinetic friction we calculated before is negative 513 newtons, so we substitute that in. And we do a little rearranging, and we find that the push force is 513 newtons in the positive direction. All right, it's not accelerating, so those two forces have to equal out. What happens when you push an object is you push a little harder to get it going, and then you don't have to push as hard to keep it going. You just have to balance out friction, and it will continue to move. A lot of kids sort of get spooked by how is it moving forward if the kinetic friction, force of kinetic friction, and the pushing force are the same. Well, you pushed a little bit harder to begin with to get it moving, to overcome the static friction, and then to keep it moving while not accelerating at constant velocity. All you need to do is match friction, and off you go. I hope this helps. Please, if you do have a question, please ask me. I'm here to help you. Use the discussion thread. Please inform your friends that I'm active on this website so they can try to do some learning. It's not perfect. We're going to make mistakes. We're going to be patient with each other, and we'll get through as best as we can under these situations. You guys take care, and I'll talk with you later. Bye bye.